Dear all, my name is İlkay Melek Yazıcı. I'm from Yıldız Technical University. Today I want to present you our study on data provenance visualization. My presentation includes these agenda topics. First, I want to give you a quick explanation about data provenance, the need for data provenance visualization, our approach on graph comparison and graph summary, and finally we have a conclusion part. Provenance data consists of the lineage of a data item from its creation until its end state by maintaining its history. As historical record of the derivation data, provenance is useful for debugging data and transformations, auditing, evaluating the quality of and trust in data, modeling authenticity, and implementing access control for derived data. We can find provenance data in many domains. The growing number and size of computational data, resources coupled with uniform access mechanisms provided by scientific workflows, allowing scientists to perform advanced scientific tasks in collaboratory environments. Scientific workflows are the means by which these tasks can be composed. The workflows can generate terabytes of data, mandating rich and descriptive metadata about the data in order to make sense of it and reuse it. One kind of metadata is provenance, which tracks the steps by which the data was derived and can provide significant value addition in such data-intensive e-science projects. Scientific domains use different forms of provenance data for various purposes. We have witnessed social media growth at an unpredictable rate in the last few years. Characteristics of social media make possible various nefarious activities that could hinder its potential growth. Social media gives users an easy-to-use way to communicate and network with each other on an unpredictable scale and at rates unseen in traditional media. Social media is largely user-generated, vast, noisy, distributed, unstructured, and dynamic in nature. It is primarily available in the form of individual users' attributes. Provenance has been studied by the database, workflow, and distributed systems communities, but provenance for big data, which we refer to as big provenance, is a largely unexplored field. As an example, large-scale provenance datasets are used to establish analytical workflow applications that have several stages in online streaming systems. Provenance information usage in the rising big data technologies might generate large-scale workflows when one considers the 3 V's of big data: volume, velocity, and variety. Additionally, the volume of gathered metadata in workflow provenance tracking can exceed the original data size. Furthermore, the collection, recording, and interpretation of provenance data play a key role in the evaluation of past, present, and future data. To get a complete view of data and discover the data values behind it, data visualization should be integrated seamlessly in the application. Data visualization is a significant area that proposes many approach to developing an intuitive interpretation of data, often through efficient visualization facilities. Effective data visualization is a significant phase in the process of maximizing perception, efficiency, and analyzing and evaluating data makes complex data more accessible, clear, and usable. If we look to the key references of this study, in Kunde's seminal work, provenance visualization components are provided with an important set of requirements for process, results, relationship, timeline, participation, compare, and interpretation. In his valuable study, Chen addressed Kunde's requirements with a customized layout and abstract view approach for network provenance visualization based on open provenance model. a visualization approach implemented for temporal provenance representation. He focused on e-science domain and worked on visual features like customized layout and abstract view. Also, a DCA summarization approach is implemented in his study. Human short-term memory is limited to hold 3 to 7 items at a time, and people can only view and evaluate a few items in their minds. Data encodings to visual channels are created through visualization so that people can view, understand, and manipulate data at any level. Visualization plays a key role in understanding information and discovering insights into data, including big data. One of this study's main motivations is to involve users in visualization. Interactive features are extended by adding grouping, sorting, and replaying features to the rearranging of features for the dynamic optimization of spatial layout to meet visualization needs. User-friendly visualization features can increase the user perception level and evaluation analysis capabilities. In this study, we provided a plugin visualization tool that implements the bold feature categories in each component class given in figure. And a novel graph comparison and summarization approach are subject to this study. W3C defined the provenance model and ontology language for the provenance data in several ways. In Prov-O specification, which is the base provenance specification for the study, has been described as the expression of Prov-DM using the OWL2 web ontology language. Prov-DM is the conceptual data model that forms the basis for W3C provenance family of specifications and defines the components that can be used to gain information about the quality and reliability of provenance data with agent, entity, and activity items. One of the key features of provenance analysis is to compare two provenance graphs. Especially in e-science domain, comparison of two graphs are crucial to detect anomalies and similarities between two graphs. In Chan's study, an improved direct classification of node attendance, called DCA algorithm, implemented for an open provenance model to compare two provenance graphs. DCA algorithm finds isomorphisms between provenance graphs by matching similar and different nodes. To do this, node attendance is calculated by analyzing each possible pair of nodes from each graph using node, edge, and connectivity attributes and properties. Chan extends DCA algorithm based on integration of both a topological description and application-specific data model. Following their approach, in this study we also provide a version of DCA algorithm for Prov-O provenance data model. The proposed Prov-O graph comparison algorithm consists of two main steps: node attendance calculation and node attendance check. The former step computes the attendance value between each pair of nodes, where one node is from the first graph and the other is from second graph. The latter step finds the maximum attendance value amongst all possible pairs. The attendance value between nodes are calculated by following the similar approach from Chan's study. While comparing the nodes, we use two different label and property, DCA label and DCA props. For DCA label, we just consider the key label properties of a node and edge components. For DCA props, we consider all available properties. Node and edge values and properties are compared at step 11 to 13, and node attendance value is computed as one result of comparison of nodes. In DCA label step 12, we compare interaction edge property as the labeled property, and in step 13 and step 18, we use the node type property as the labeled property for comparison. In Prov-O specification, node type refers to basic types agent, entity, and activity, and interaction refers to property like was generated by, as shown in Pro O specification. For DCA probes, we consider attendance-based comparison. In step 8, we initialize the default attendance value to fully match the attendance value as 1. In step 12, 13, and 18, we update attendance value according to comparison property using its weight coefficients. In the node attendance value calculation, current edge and node properties are given more weight than adjacent node properties. By adding step 19, we consider node's incident edge count for comparison. In step 8, we initialize the default attendance value to fully matched attendance value as 1. As shown in equation 2, we first calculate max weight value for node comparison using weights value explained in table 3 in order to use as a normalization value in equation 1. For total weight calculation, we get full node property set and edge property set sizes of compared node pair. Maximum weight is initialized as if all node and edge properties are identical, and in each comparison we decrease the updated attendance according to unmatching property weight. In our experimental results, we test our DCA algorithm by using different weight sets which are shown in table 3. This step is only an issue of DCA probes approach. In Chan's version of the DCA algorithm, the node pair that has maximum attendance is get as starting point, and each of their adjacent nodes are compared with a predefined threshold value in a greedy approach. In our improved version of node attendance check, the attendance combinations are sorted in descending order, and the pair with maximum attendance is marked as first similar nodes. In attendance threshold check, we just consider unmarked nodes. In our study, we defined threshold according to our experimental results and set it to 1.8 for attendance check along the comparison process. In our experiments, we use graph 1 graph data has 33 nodes and graph 2 graph data has 30 nodes of probo activity, agent, and entity items. In DCA label experiments for the graphs, which key property-based ground truth values are shown in table. We get 100 accuracy of comparison performance, which is visualized in figure on left side. For DCA probes algorithm, we use the same graph 1 and graph 2 graph sets, which property-based ground truth values are shown in value. The experimental study on the use of graph comparison algorithm are done separately using two different weight sets, weight set 1 and weight set 2. In DCA probes approach, we get experimental results by using different weight values for node edge and adjacent node property comparisons in two different weight sets using our sample graph shown in weight table above, and the results are visualized in figure left. Experimental results table shows that by using the weighted property approach in our graph datasets, we increase comparison accuracy compared to Chan's version of DCA approach because of the greedy approach that stops iterating nodes if there is an unmatching node pair and ignores the remaining nodes. In this study, node pair comparison is improved using weight threshold and by considering the node's neighbor node and edge features. Node weights are generated in node's neighbor and node's edge levels as described in table. For graph summarization, we propose a summarization methodology to generate short summaries for Prov-O compatible large provenance graphs to gain a better understanding of their characteristics. Especially in social media domain, data is rapidly growing, which data is distributed, dynamic, heterogeneous, and includes noise. When the data is considered by summarization of social media provenance data, effective and user-friendly visualization is generated. Prov-O data model defines agent, activity, and entity items and their attributes. For summarization, we focus on feature-based centroid clustering approach. To illustrate the use of centroid-based clustering for summarization, we use K-means algorithm, which is the novel and popular cluster analysis in data mining, which K-number is predefined before summarization. To analyze the workflow and to find time-based patterns in provenance data for clustering nodes, we simply use the occurrence time feature defined by Prov-O model. In general, provenance data activity item has occurrence time. In this study, considering the provenance data entity is the key interest of user about the data history, we focus on data-centric occurrence time attributes of activity item as it is defined by Prov-O data model. As shown in pseudocode here, we first get entities in sorted order from activity items in provenance data. In step 6 to 12, we are generating clusters based on entity occurrence time and setting related agent and activity nodes for an entity item. In step 10, in order to prevent from overlapping in clusters, we are locating each item into the visualization frame with a random behavior. And as a result, we tested our summarization results on a test graph that has 80 nodes, including entity, agent, and activity items. We set up our clustering parameters and K-means value to 4 for test purpose. We evaluate our unsupervised clustering performance by using F-score metric. As expected, the results showed that the use of occurrence time attribute for clustering of provenance nodes lead 100 accuracy. In future work, we are planning to improve Prov-O data summarization by considering new Prov-O features and optimizing K-number according to dataset in the visualization prototype and to work for a new clustering methodologies for effective summarization. We will improve our graph comparison approach by considering the feature importance for related domain. In addition, we are planning to develop a real-time provenance visualization approach for streaming provenance by taking advantage of emerging big data and messaging technology stacks like Redis and Kafka for real-time notification. Our key references that are mentioned in these presentations are shown here. And this is the end of my presentation. If you have any comments and any questions, please find me to the attached mail. Thank you for your kind attention. Thank you.